I actually have a PowerPoint presentation for you.
You're not going to draw on the board? And
No. At least maybe. I hope not.
Actually, the PowerPoint is just drawings of the board.
Actually, I did this lecture before and I took pictures. I like the drawing on the board.
Yeah.
It's interactive, right?
No, there are very few lectures that are PowerPoint.
Yeah, all right. So I don't think there's anything to review today. Last time we finished up talking about, I don't even remember because my brain is scrambled. So I'm not even going to write down the review on the agenda because I don't know what the hell we did. Oh, we started talking about multiple regression. All right. So what I want to talk about today are things like causality at Christmas. So it's February, so let's talk about Christmas. And then let's get back to hypothesis testing and experimental design. Because this is sort of a step back before we go very deep into regression, so that we get an understanding of how your study design and your statistics go hand in hand. You could have the most elegant, beautiful statistics in the world, but if your study design is poor, your statistics are for naught. So really, we learn about the world not through the statistics, but through the questions we ask and the design of our studies. So that's sort of my whole takeaway from this discussion today. So let's talk about causality in Christmas, right? So we talked about three things before that were necessary to establish a causal association. Does anybody remember what those things are?
Temporal relationship.
Temporal order, right? What does that mean?
The one has to come before the other.
Well, that's not very descriptive.
The causal thing has to come before.
There you go. That's better. Thank you. What's this?
Is space validity one of them?
Well, that's validity. So it gets that gets to our inferences.
Covariation.
Covariation, right, which kind of gets to the inferences that we're talking about. And the third thing that's necessary to establish a causal association is what? We need to rule out alternative explanations for why we see what we see. And it's the study design that addresses that third thing. So cause coming before the effect, that's a study design thing, right? In an observational study, that's a difficult thing to do, but in a planned study, you can do that. This idea of covariance, that is what it is. That's purely a statistical thing, and we talked about the assumptions that go in our models and what happens if we violate the assumptions of our models. Then our inferences regarding the covariation become wonky. But the third thing is actually the most important thing, ruling out alternative explanations for why we see what we see. That's all about the study design. So what we want to talk about, people are like, Tim, you're crazy, we get that, but why are you talking about Christmas when we talk about causality? Right, so are you guys familiar with these two stories? So we have A Christmas Carol and It's a Wonderful Life. And there are two common themes in those movies. Have you seen those? Right? Can anybody describe what A Christmas Carol is? For those people who don't know what that is? Nobody?
An old businessman who is very mean to all the people in his life. Is visited by his old coworker who says, you better shape up or you're going to end up in hell like me, and let me show you why. And then he's visited by three ghosts. The ghost of Christmas past, the ghost of Christmas present, and the ghost of the future.
So let's talk about the ghost of Christmas future. What is the significance of the ghost of Christmas future?
This is what's going to happen if you keep going like you're going.
So that's the comment, that's the idea here. If you do this, then this will happen. If you change your behavior, then something else could happen. Right? And how about It's a Wonderful Life? Does anybody know that story with George Bailey and Clarence? I always get
do that one.
You want to do that one too?
Anybody else?
We have Siskel and Ebert over here.
Okay, another So George Bailey is a small town guy who dreamed of leaving his small town and seeing the world, but the circumstances of his family life made him take over the family business so that his brother could go marry the woman he loved, and then his father died, so he had to take care of the business, which was a savings and loan. And he really helped the town out during the Depression, and did a lot of good things for the town, but it resulted in his business not doing fabulously well. So at some point, all the things are going really bad for him. His uncle loses the money that he needs to deposit in the bank, and
Because there's an evil villain.
because there's an even because Lionel Barrymore is really bad. And so then he's like, oh gosh, everything is so bad, I wish I had never been born.
I wish I had never been born. So
then he almost kills himself. But then Clarence comes, and Clarence is
not yet an angel. He's not yet an angel.
He's a pre-angel, and he shows George what life in the town would have been like if he had in fact never been born.
So that's another case of, if this didn't happen, then this would have happened, right? So those are two cinematic examples of what philosophers call a counterfactual. Right? So when you talked about propensity scores in Andy's class, did you talk about the concept of counterfactuals and potential outcomes?
Mm-hmm.
Okay, so counterfactuals are what would have happened had not what happened happened. Okay? So this begs the idea of something that we refer to as counterfactuals. Right? All right, so let's talk about this idea of a counterfactual. So this is a lecture I actually give in the School of Education, and they get it, so I'm going to assume that this is going to work for you since it's right in your wheelhouse. Right, so here we're going to talk about the effectiveness of a new drug, right? When you talk about effectiveness, this begs the question, effective as compared to what? Right? Because if you just, let's say that you guys are all very high achievers, you've taken the test and you got a 4 on the test. How did you do? Well, what if it was an AP? Remember AP from high school? If you did an AP, how'd you do?
No, that would be if that might be for a 3. I wouldn't jump for a 4.
Right. Right. But the idea is to answer these questions or to address these questions, you have to have context. Right? So when we talk about effectiveness or something like that, we have to ask the question, relative to what? As compared to what? Otherwise, there's no context in which to evaluate your evidence. It's just a number. Because without something to refer to, how do you answer something? It has no meaning, right? Okay? So, if we're going to evaluate the effectiveness of a new drug, we want to compare it to something new, right? And because we're unethical Americans and our FDA is so screwed up, they require us often to do placebo-controlled trials. Doesn't happen in other countries, but in the U.S., we're so advanced we actually withhold treatment. That's my editorial. Okay. All right. So this is what I was talking about. So when we talk about causality, we have to think about it in relative terms. If you didn't do this, what would have happened? The counterfactual. George Bailey and Ebenezer Scrooge. Okay? So, we have to have this concept of potential outcomes. Potential outcomes. So we have to introduce this notion of potential outcomes. And I think physicists like this. Are you guys familiar with Schrodinger's cat? Or so the cat, is your cat alive? I don't know. He's both alive and dead, and we'll know when we look. Right? Because the act of observing, the physicists say, actually causes the cat to be alive or dead in the radioactive box. Right? So it could be both. Right? So we have to introduce this concept of, if you do this, if you choose this path, If you go down this fork in the road, there's this potential outcome waiting for you at the end. If you go down this fork in the road, there's another potential outcome. They may be the same outcome, but the idea is that they are potential outcomes. And you don't realize those outcomes until you actually choose your path. Right? Which brings up a problem. The problem is what's the problem with that? Anybody see the problem with this concept of potential outcomes? Can anybody be two places at once? So we call that prima facie individual outcomes, right? That's the prima facie individual effect, right? So we actually can't see individual effects. They're not possible, right? And even if we were to do, you talked about experimental designs and you have crossover trials and things like that. Well, what happens in a crossover trial, we have things like maturation that happens. People simply change as the passage of time. Even if you guys may be delivering the intervention, you are the instrument of the intervention. The instrument, changes over time. So you're not the same instrument you were at the beginning of the study as you were 6 weeks into the trial. So there's variability that goes into that. So it's not the same person. It's not the same procedure. So there's all of this variability, all of this changing that goes on. So it's impossible for us to see these individual effects. Okay? It's impossible to do that. But if we could, let's say, for example, that we have some new drug, and these are the potential outcomes for you, right? If you were to take, your old drug, this would be your outcome, right? And let's play God here for a minute because we're doing mathematics. I'm going to do the mathematics, and we can know the truth, right? So let's deal with a little bit of theory here. And let's say theoretically that if you took the new drug, your outcome would be a 25. So let's say that we could know that because we're gods, right? If we're gods, that we know the potential outcomes. So if we knew your potential outcomes, we could actually see your individual causal effect. Right? We could see your individual causal effect, and that would be a decrease, a relative decrease of 50. Right? It's a relative decrease of 50. So this brings up another thing here. A lot of times people will say, yeah, but I'm interested in change from baseline. That's a very common thing that we're interested in looking at in science is change from baseline, right? So people will go, oh, okay, so what I'm going to do is I'm going to subtract my post-test score from my pre-test score, get a difference, and then subtract my post-test score from my other pre-test score, get a difference, and look at the difference in differences, right? One thing you'll notice is that difference in differences is the same as had you ignored the pretest. Right? Which brings up another teaching moment with respect to experimental design. In experimental design, I don't care where you start. I care where you end up. So let's talk about that for a minute, and just for you guys, I'll write on the board. So if I were to do a large randomized trial, large, I don't know what large is, but let's say that it's a large, and I'll use a different color so maybe it'll show up on my thing. A large randomized trial, do you guys know what kind of assumptions that allows me to make? The fact that I'm using random assignment to put people into one group versus another group? Right. We can make the assumption that the groups are equivalent. It's the concept of equivalency, right? That becomes a very important assumption. And let's talk about that for a moment. Why can we make the assumption that the groups are equivalent at the beginning of a study if we use random assignment to create those groups?
Let the unmeasured stuff is equally distributed.
Right. Right. Well, we assume it's equally distributed because we say the mechanism for the creation of those groups, and this is where we begin to learn about things, and this is a very important point. The mechanism that gave rise to group 1 versus group 2 was chance, was random. And by definition, anything that is random cannot be associated with anything else. All right? So at the end of this discussion, we're going to talk about something called probabilistic equivalence. Okay? So in the beginning of a study, let's say that I have one group and they start here, and because I'm using random assignment, I can reasonably make the assumption that the other group also starts there. Right? That is a very reasonable assumption. And statistics is built on, statistical inference is built on this assumption of equivalence. Remember we talked about the central limit theorem? And the central limit theorem predicted that the mean of my means will equal the population mean. So this is how random assignment works. It ties in very nicely with the central limit theorem. This says that on average, if I were to replicate my study using random assignment, the on expectation, that means, we've had that word before, expectation. Remember we talked about expected outcome as opposed to average. I'm encouraging you to think of it that way. On expectations, the outcomes will be unbiased. And what that means is that on expectation, on average, outcomes from randomized trials will be correct. Does that mean any given study will be correct? In the sense that it gets mu? No. No, we don't. No, it doesn't. And that gets us back to the idea of statistical inference. It doesn't. But because we use random assignment, our groups were made up based on chance. So any bias, any selection bias, is removed from that equation, from our model, because a person is in one group versus another, not because they're male or female, not because they're rich or poor, not because they're good looking or not. It's due to chance. Random assignment takes away all of that bias, all of that selection bias, because it's a lottery system. It's chance that makes up that group membership. So let's talk about this here. Let's say, I'll draw this here. So both groups start off at 80, and then at the end of the study, one group drops down to 25, and the other group drops down to 75. All right? Incidentally, if I just had data that looked like this in one group, you went from an 80 to a 75, would you say that your intervention worked?
I don't know what would happen to that.
Oh, really?
You don't know how good or bad that is.
In one group. I assert, I posit, I put forward to you, I propose to you that when you have a one group design, this change is completely uninterpretable. Because I don't know what gave rise to that change. I don't know what gave rise to that change. Remember those alternative explanations that we were talking about? I haven't ruled anything out. The only thing I can say is that they went from 80 to 75. Why? I don't know. I don't know. And some people would say that this is effective. Right? This is effective. But now that I have this piece of information, this other group went down to 25, now we can say something. And oh, by the way, if I do 80 minus 75, and then do 80 minus 25, what's that? That's going to be, 55? This gives me the same answer as this, as the difference in differences. And because I make the assumption that they're going to be equal at the beginning, I don't care where they start. I don't need to. Look at that. In biological processes, we often don't much care about this, But the kind of things that we study, and we're not studying people in laboratories, even though we may be studying lab values. There's lots of things that go into people's laboratory values in addition to treatment. Other things like behaviors will go into lab values. Right? If I'm looking at cholesterol, for example, I could give them an anti-lipemic medication, but that person, in addition to taking the medication, could change their diet, they could exercise. Right? So that alone could change the outcome of their lipids. Right? So even though I'm taking a laboratory measure, this pretest that I give them introduces a bias. It potentially introduces a bias that we refer to as testing. You know? The fact that people are being observed is often enough to significantly change their behavior. Right? So when you're designing studies, think long and hard. Do I really need a pretest? Because I could be introducing a testing bias, which could influence the behavior, which is an alternative explanation for why I see what I see. Okay, all right. Okay, all right. So let's pretend for a moment that we're gods. It's fun to play that every once in a while. I don't get to do that very often unless I'm doing math. But let's pretend that we're gods for a moment. And being gods, one of the definitions of God, being a god, is that you're omniscient. You know everything. So in this case of knowing everything, we, as gods, are privy to everybody's potential outcomes. Okay? We are privy. We know everybody's potential outcomes. So we are sitting in the Pantheon somewhere, or wherever. We're sitting in a crucible or something. And we're looking down on, these foolish human beings doing clinical trials because, they don't know what we know. They have to do studies, but we're gods. We know everything. So here we're going to look at survival time after surgery. Right? So we have standard surgery, which is going to be represented with Y1. And we're going to look at a new surgery. I'm sorry, Y0 is the old surgery, Y1 is the new surgery. Okay? So looking at this, because we are gods, we know people's potential outcomes on all of the, for everybody. So what I can look at here is the average causal effect. The average causal effect. So if I knew everybody's potential outcome, I could get the potential difference and say, on average, is the new surgery better than the old surgery? And I'm looking at this, we're looking at this because we're gods, and we know, you know what? On average, the new surgery kills people 2 years sooner had they been given standard of care. How does that feel to be a god? Right? It feels pretty good to be a god. That's pretty so back, we know that stuff. If you knew this in your, okay, let's step back for a moment. Now we're mortals again, and you're in your daily practice. Right? If you knew this, would you make any errors in your decision? No, because you know, well, for this person, I know the best outcome. And for this next person, there's something different about this person, so I have to give them the other treatment, even though on average it kills people. But for this person, the new therapy is best. We don't know that, right? So by understanding the process that gives rise to the data, we begin to learn about things. Okay? Now let's say for a minute, instead of being gods, you're perfect. That's kind of nice. And in making your decisions, I mean, this is sort of what you do every day, is you have to make decisions about what intervention to give to each of your patients on an individual basis based on the evidence that's presented to you and the state of the art of your discipline. Is that a fair assessment? Right? So you basically make idiopathic types of decisions. We don't like to hear that, but we do. And believe it or not, human beings are actually very bad at making decisions because we have shown study after study after study, time after time, that the same person given the same information on different days will make different decisions. And this is particularly rampant in medicine. We've done a lot of studies in medicine that does this. But let's look at this, for example. Because you guys are so awesome. And I'm not pandering, I'm trying to make a point. You guys here are so awesome. When you decide to deliver your treatment, you decided for this first person, this person should get the new treatment. These guys should get standard of care, and these two last guys, they should get the new treatment. This is an observational study because you selected the treatment for the patient. And at the end of the day, you say, okay, well, the average life for people who received the old treatment was 5.4 years. The average years of life for the people who got the new treatment was 11 years. What is the inference based on this observational study? The new treatment is far more effective than the old treatment. Right? We know that because we're perfect. We always make the right decision. Is that the right answer, though? So the average, so this says that the new intervention increases life by 5.6 years relative to the old treatment, on average. Is that the right answer? It's not the right answer. This is selection bias. Right? This is an observational study. This is what happens when we don't think about the mechanism, the process that gave rise to who received what. If we ignore that process, then our inferences are biased. Could be biased. Could be biased. Doesn't mean that they are biased, but our inferences could be biased. And you know what? The thing about bias, that it's really hard to tell. Okay, so the idea here is again, understanding the process that gave rise to the data helps us make inferences about the data. So remember I talked about random assignment giving us the right answer on average? Okay. So in our study here of, I think there were 1, 2, 3, 4, 5, there were 8 subjects in that, you got 8 patients. So here represents all possible permutations. These are, if I could go back in time and repeat my study for every possible way, these would be the outcomes. So let me explain how you read this chart. So if there's, I have patient 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, right? These ones represent whether or not they received the new surgery. The 0 represents whether or not they received the old surgery, right? So when I do, if I were to do a random study, conceptually what I'm doing is I'm reaching into this bag. Because all of these studies are possible with random assignment. And what I'm doing is I put all these studies in a hat, I've shaken them up, I'm closing my eyes and I'm pulling a study result at random from this list. That's conceptually what I'm doing. Conceptually, the gods, insert your god's name here, knows all possible outcomes for all possible studies. Right? So if you were to do a particular study and you got this outcome, here you get an average effect of 1.6 that says that the old intervention yields 1.6 years more life relative to the new intervention. Is that right? It's not right, but at least it's in the right direction, right? And at random, I could have gotten this outcome. This is the outcome that we saw on the previous page. That at random, I could have pulled that outcome, which says the new intervention is far more effective than the old intervention. So look, and this really is all permutations of the outcome. So this is 8 choose 3, if you remember those combinations. Right? So let me ask you this. Would you ever trust the results of a single study? Even if it was a really well designed, it was an enormous study, thousands, tens of thousands of people? Can you trust the results of a single study?
We do.
Huh?
We make decisions based on, I mean, we like.
What if you got this? What was this? This was your gigantic study, your multinational, multi-site study with 50,000 patients in it. It's a pretty impressive sounding study, isn't it? Right? Lots of evidence to suggest that the new intervention is superior to the old intervention by a wide margin. One study. If you were gods, you would go back and you'd say, what would happen if I averaged all of the outcomes over all possible studies? What do I get? I get the real average treatment effect. We call this the ATE. Right? And what does this say? This says that the average of my averages gives me the right value. But if I don't use random assignment and I allow selection bias to happen, I could get this result. I could replicate this result with the same type of selection bias.
So what's the magic number to average over?
There's no magic number. That's not how science works. That's not how science works. Right? You want the scientific answer or the FDA answer? The FDA answer is 2 well-controlled randomized clinical trials. That's the answer. That's the FDA answer. But now you guys are being educated. Bless you. Is it okay if I write on the board again? Fine. So here, what we're doing is this is going to represent our sampling distribution. This value, I'm just going to write that as the Greek letter theta. This represents the real outcome, right? It's possible that with my 2 well-controlled, randomized clinical trials, that I sample here. It's possible, isn't it? It's possible that I sample from here. And then I have to replicate it because, oh my God, this is so good, let's pour more money into this. And I'm going to replicate it, and I happen to get, by chance, this result. I think this is the second largest result. It's not as impressive as the first one, but you know what? It's still evidence that suggests that the new intervention is a good one. This is what the FDA would say, go forth and multiply your millions.
I mean, this is only okay if, like, you're perfect and you know that it's 2, right? Because,
Pardon?
I mean, like, this only, like, because theoretically, like, the one that you're saying is wrong could be the right one.
Could be the right one.
Right?
Correct.
So, I mean, like, there would be some logic to looking at this and saying which is the most frequent.
But you don't know this.
Right.
You know, which gets back to your question of when do we stop? Right? Because it's possible, although statistically not likely, that you would get 2 results in 2, quote, well-controlled randomized clinical trials that are out in the tail in the wrong direction. It's unlikely, but it's possible. Like a monkey coming out of my butt. It's possible, but rather implausible. So what would you guys do? What would you guys do? What would you recommend? Because we don't know this. We're humans. We don't get to sit at the Pantheon.
All you can do is counsel the patient.
No, we're scientists. We're not physicians. What would you do?
Get a confidence interval.
Doesn't matter. The confidence interval still sets it, and it doesn't include 0.
Well, you want to try to do something smaller that can estimate those?
Say that again?
You want to try to do something that can estimate those?
You would try, yeah, this is what we do with statistics. We try to estimate this.
So you need more studies.
You would do more studies, that's the right answer.
And then it's acceptable that biax kill a bunch of people because that happens.
I don't know, from my perspective, I don't know about you, as far as I'm concerned, Viax should not have been taken off the market. I'm serious.
They should have just been
From your
like more
from the
forthright about, like,
Well,
I
there's
mean,
that. Assuming they were forthright about that. I know the people who made those decisions, they're scumbags. But assuming for a minute that all the evidence was out on the table, assuming for a minute all the evidence was out on the table, I would argue that for a large group of people, that drug was awesome. And for a very small group of people, the drug was toxic and deadly.
I mean, I think it still would be on the market if there hadn't been like the cover-up of it.
I don't know, so we made politics make health decisions for us?
If you read the original paper, like, if you really read it, they just assume that NSAIDs are sort of protective rather than like Vioxx being dangerous.
Yeah, all right. Right. But again, this is how statistics works. This is how statistics works. So the idea here is even if I were to do a randomized study and I were to get the worst wrong result, because we used random assignment, is there selection bias? Did randomization fail? You can tell by my body language what the answer is. No, this 5.6 is still an unbiased estimate. It's unbiased because the process that gave rise to that number was random. So what do we do? Because I'm not going to trust the results of a single study. I'm going to rinse and repeat, which sounds like the scientific method. Observation, codification, prediction, hypothesis testing, keep doing it over and over and over. And this is why we continue to do studies over and over and over. And this is why never shall pass my lips, this is valid. Things are not valid, as in yes, no. We have evidence of validity. There are many different types of validity for which we can generate evidence. Things are not valid in an absolute sense. Things are valid for, more or less valid for different things. So we talk about what is the degree to which our inferences are valid. Because guess what, over time, I don't know about you, I've been doing medicine for about 25 years now, studying medicine. Effects that we saw in the 80s in psychiatry have all gone away. Same drugs. How the hell is that possible? What, have we evolved as an organism so much in 30 years that old drug that had massive effects we no longer see? I don't believe that. I mean, it's possible, I suppose. There's the monkey. But I don't think it's plausible that our species has evolved in such a way biomedically, biochemically, that drugs that worked 30 years ago no longer have the same effect as they did, today as they did 30 years ago. Something else is explaining what the hell's going on. Okay, so, this idea about understanding the process that gave rise to the data. If it's not random, then guess what? There's always the possibility of selection bias. There's always alternative explanations for why you see what you see. Always. When you use random assignment, you have a theoretical basis upon which to make the assumption that groups are equal, even though they may not be. Because the process that gave rise to that inequality was chance. And I don't care about chance, because chance is not going to be correlated with it. Okay? So let's talk about null hypothesis statistical testing a minute. We've seen this before. We write our null hypotheses, our statistical hypotheses in Greek because we're talking about populations, right? This is when our statistics go from descriptive to inferential. When things go from descriptive to inferential, we go from the specific, or sample, to the general, the population. This is the hypothesis. We test the null hypothesis. We test the thing that we don't want to be true. Right? And because of that, is because science, we can't prove anything using the scientific method. Right? If you study the philosophy of science, the history of knowledge, everything that we see around us is fake. It's not real. It's a construction that we've created in our minds. So how do we know what's real? I'm not sure. Right? My reality is different than your reality. We can look at the same thing. We can describe it using the same words, but I don't know what the hell's going on in your brain exactly. We may represent this differently. It's a social construction through language. Okay? So we can't prove what something is in science. So if you want, we talked about the BS meter. The BS meter in science, as soon as you hear somebody say, we have proof, or we have proven, the BS meter goes up and goes, whoop, 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 whoop. Right? Right? This is obviously somebody trying to sell you something. They're trying to sell you something because, we did a large university study. A large university study. Could have been unbiased, but still, could have gotten that implausible answer by chance. Okay? In science, what we do is we don't provide evidence for what something is. We provide evidence for what something is not. So think of science as an onion. Right? We have chefs in the room, cooks in the room. What happens when you peel an onion? I didn't expect a smart-ass response to this. Okay, now I've recalibrated my expectations with you. What happens as you're crying? What happens? You peel a layer, then and then you peel that one, and then finally you get to the little pulp, right? The thing in the middle, right? Right. Well, think of science that way. I'm ruling out alternative explanations. It's not this. 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 Not any of these other things. So if I'm ruling out all of these other things, then the only thing left must be the thing that it is. So we don't provide evidence directly for something. We provide evidence indirectly for something. And the reason for that is actually kind of simple. To prove something, you have to prove it for all cases, which is theoretically possible, but logistically impossible. To prove what something is not, you just see that you need a single exception to prove something not true. Just a single exception, that's it. That's far easier to do than to prove everything, all cases. Right? So we write down our null hypothesis and our alternative hypothesis, and this is the thing that we hope is true, but we don't test it. Which kind of makes a lot of sense, right? All right. So there's this guy, Jacob Cohen. He was one of my favorite authors. He was a curmudgeonly old psychologist at Columbia in NYU. So he wanted to change the name of null hypothesis statistical testing. Have I told you this story? Now, he wanted to change the name of it from null hypothesis statistical testing to statistical hypothesis. You don't have to write this down. You can if you want, because it's actually in a journal article. Inferential testing. That's what he wanted to call it. He wanted to call it that. Because actually what we're doing is we're not answering a question that we're interested in. We're really interested in this, but what we do is we address this. Okay. Okay, all right. So here's our chaos table, which I'm sure you've committed to your brain, right? So we won't spend a whole lot of time on it. But the thing I'm trying to get into you guys, to impress upon you guys, is this fallible humanness. Everything that we do has some degree of error in it, right? So we have to acknowledge that. We acknowledge that when we write down our models, right? And the other thing here is now we're acknowledging our fallibleness in the judgments that we make. There are probabilities that we can be right and probabilities that we can be wrong in making our decisions about the data, about the world. So I don't know if you've ever seen a graph like this, but this is actually what we do with hypothesis testing. So when we talked about hypothesis testing, either the null hypothesis is true or the null hypothesis is false. It's not an or, it's not an and situation. Either the null is true or the null is false. Make sense? So if the null hypothesis is true, for every study we do, regardless of the quality of the study, be it a really well-designed randomized clinical trial or a really poor designed observational study, every study that we do is pulling a result from the null distribution. Right? So it's possible that if I pull a result from the null distribution, I get a score way out here at 5. When the null says that there's no difference between the groups, I can still pull a 5, right? Yeah? It's possible, but it becomes implausible. But even if I pulled this 5, right, I have to make a decision. I have to make a decision because I don't know if my data came from the null distribution or if it came from the alternative distribution. So I have to make a decision based on the incomplete information that I have, which has error in it. So I have to decide, did this 5 come from the null distribution, or is it more likely that it came from the alternative distribution? All right, this is rocket science here. The baby can get this. From which distribution did this 5 most likely come from? The null or the alternative? It most likely came from the alternative. But is it still possible that it came from the null? Right? It's not plausible that it came from the null. It's more plausible that it came from the alternative. So do we know if we're right? We can't know if we're right. We don't know if we're right. Incidentally, this is what alpha and beta look like on these distributions. So when I talk about alpha errors, remember the table that I put up very quickly, is that alpha is only in the null distribution. Whereas beta, which is the probability of failing to reject the null hypothesis, the beta only belongs to the alternative distribution. Okay, so let's talk about a p-value. Because now we're going to start getting, yes, sir.
Sorry, when you were talking about like the 5 value, does that kind of how you think about the outliers?
Well, it is in a sense. It's an outlier in both of these sampling distributions.
Yeah.
But because we don't observe these, we don't know it's an outlier. We can't know it's an outlier.
So are you making a case that you can't throw out outliers?
No, in this case, this is a result of a single study, not an observation, but it's the result of a single study. So this 5 is but a single point in my sampling distribution. So the idea here is how do I get a better sense of from which distribution did this 5 really come from? Well, what we do is we replicate our studies. All right? So if the data were to come from the null distribution, if I were to replicate my study a whole bunch of times, what would happen is I would have a negative 5. I would cancel that positive 5 out. Because a 5 and a negative 5 makes a 0. Which on average gets us to the right value. So this is what we do with meta-analyses. Since we can't observe the theoretical sampling distribution, when we do meta-analyses, we build what's called an empirical sampling distribution. We actually go out and collect data, and we try and get a better sense as to what this sampling distribution looks like by actually looking at outcomes. And we combine these outcomes of our studies. Okay. Okay. So what's a p-value? These almighty p-values. You've seen these things in articles. We get excited when they're small. Size matters. When we talk about p-values, I think people get excited. That's a tiny p-value. What's a p-value? Come on, take it.
probability your study, oh, you don't like probability, right?
No, it's a probability. That's what I told the P.
Probability that your study's in the tail.
Probability that studies in the tail. That's close. So let's think about it this way. So you guys know this. Let's put this in language that you understand. So let's assume that we're sampling from the null distribution, right? Because that's actually what we test, right? We assume that the null hypothesis is true. That's what we test statistically. So if I were to draw my sampling distribution, the null distribution, can you describe to me what that would look like? I know you can. It's a sampling distribution. Think central limit theorem. It would be normal-ish. Good. It would be normal-ish. And let's write down the null hypothesis. The null hypothesis says that mu1 equal mu2 or mu1 minus mu2 equals 0. These are equivalent, right? Right? So what is my expected value of the sampling distribution of the null? 0, right? And let's assume that I have an infinitely large sample size so that my t distribution looks like a what? I'm sorry, my z, I just gave the answer. My t distribution looks like the z distribution, right? So what do we know about the standard normal distribution? The standard deviation is 1, right? What percentage of the scores fall within plus or minus 1 standard deviation? Do you guys know that? That's 68%, right? So 68% fall within plus or minus 1 standard deviation, leaving how many outside of 1 standard deviation, beyond 1 standard deviation? 32, right? So here's, okay, so what happens, what percentage of the scores, or what's so special about 1.96 on the standard normal table? Yeah, so here is the, I'm going to write down the percentiles here. 84, 97 and a half, 16. So these are the percentiles. Okay? So if I did a test, and my t statistic with an infinite number of degrees of freedom was negative 1.96. What's the probability that I have a z-score with an absolute value of at least, let me say that again, absolute value of greater than 1.96?
5%.
It's actually less than 5%, right? Does that make sense? Because there's 2.5% here, 2.5% here, and I'm saying less than, right? Okay, right? That's what a p-value is. So a p-value is the probability of seeing an effect as large as I did, probability of seeing an effect at least as large as I did, that way we can go out in the tails, assuming the null hypothesis is true. That's how we interpret a p-value. So we assume the null hypothesis is true, which is why I keep talking about possibility versus plausibility. If that p-value we're saying is less than 0.05, that's our alpha, right? That says that we're willing to take a 5% chance that we're going to make a type 1 error, and we're going to decide, you know what? Since our p-value is less than our alpha, our decision rule is that we are going to conclude that the data have most likely come from the alternative distribution. Right? It's implausible that this value came from the null distribution. It's more plausible that it came from the alternative, while still acknowledging it's possible. Right? Because let's say I had a p-value of 0.001. What's the probability of making a type 1 error? It's still alpha, whatever you decide alpha to be. Right? So that alpha that we make is simply a decision level. It's simply a threshold by which we decide whether or not to reject or fail to reject a null hypothesis. That's all it is. It's just a decision threshold. Does that make sense? We talk about plausibility versus possibility. Possible and plausible. Right? So let's, so now we've talked about what a p-value is. Let's talk about, well, that's what it is. That's what I did. So the other thing we want to take into account here are, don't be seduced by tiny p-values. Right? Tiny p-values. Everything else being equal, we started talking about this yesterday with sample size calculations, and I'll actually show you the formula comparing two means. Everything else being equal, a small p-value in general usually tells me that you have an enormous sample size. So might I say that a small sample is compensating for something? Or a large sample size is compensating for something, right? P-values don't tell us about the probability of being able to replicate an experiment. Right? This is a common misconception as to what p-values. They are not. All right? They also don't tell us the probability that the null is true. The null is either true or it's not. So the probability of the null being true is either 0 or 1. It either is or is not true.
Is that point about the p-value does not tell us that we'll be able to replicate results, all about the sampling distribution?
Yes. Right. So if I get a p-value of 0.00001, it doesn't tell me anything that I'll get that in. This tells me how far out in the tail was that result. That's all it tells me. Assuming that the hypothesis was true. Okay, so look, we talked about this yesterday a little bit. We started talking about this. We started talking about practical significance. And what I would encourage you to do is think about how big would a change need to be before it would influence policy, before you would change what you do. You know, the example we gave yesterday was, let's say that we did a study and we compared a new drug versus an old statin, an existing statin, and the new drug on average decreased cholesterol by 1 point. With a p-value of, it was an orgasmic p-value, so there were lots of O's before a non-zero number, right? Would lowering, on average, lowering someone's cholesterol by 1 point, what, are you impressed? It had a tiny p-value. Why aren't you impressed? You got to be impressed, man. It had a tiny p-value. It's tiny. Got to be good.
Well, I mean, I personally want to know if the outcomes actually were better beyond cholesterol.
Okay, they were. No, they were the same, but it reduced cholesterol.
Then I would not be.
Well, let me ask you this question: Would you expect better outcomes as a result of lowering cholesterol on average by 1 point?
No.
No. So you would say maybe then that 1 point statistically significant change was statistically significant, but not of any clinical importance, or what I'm referring to as practical significance. Yeah. So we want to make a distinction between those things, right? Okay. Okay, so the next thing we need to talk about are things called effect sizes, which you already know a lot about. Right? There are two types of effect sizes, and the one that you know about a lot are correlative effect sizes. So correlative effect sizes, ooh, that's a fancy letter. Ooh. This is the Greek letter eta, ETA. You've seen this before, sums of squares of sum effect divided sums of squares of total. This is an R squared. This has got a P. What do you think that is? That's here. A couple of weeks ago we talked about partials and semi-partials. This is the partial R squared. Right? You know about this stuff. This is the Greek letter omega. This is an omega squared. This omega squared we interpret just like we do this eta squared, which is an R squared. The reason that this omega squared was developed is because what we know is with small samples, R-squares are biased. R-squares are biased high. So what's a small sample? Say less than 50. Most of the studies you do will have tens of thousands of people in it, I suspect, doing policy type research. Okay. And the other thing we have here are standardized differences. Here's Cohen again. So let's look at this. I have the difference between an observed value and, say, an expected value. Then I have two variances divided by 2. So if I take two variances and divide by 2, what do I get? Average variance under a radical. So it's a square root of a variance. Standard deviation, so I have observed minus expected divided by a standard deviation. That's a z-score. So Cohen's D is the difference between two groups in standardized units, in z-score units. Okay. Standard deviations are good because then we can compare the results of one study to another study without having to care about the metric in which the thing was measured. I might do a diabetes study where I look at HbA1c, and another study where I look at glucose. Well, obviously the things are going to be in two different scales. How do I compare the results? Ask Sarah, she'll tell you. Okay, all right, I'm going to avoid this. On the slide deck, there are threats to what we refer to as statistical conclusion validity. Remember we talked about validity, we talked about conclusion validity, internal validity, external validity, and construct validity. I'm gonna let you read all this, but conclusion validity deals with the extent to which we decide that the relationship, there is a relationship. So it deals with that covariance concept in causality. The other thing that we started talking about yesterday, well, let me do something else and then I'll go backwards. This is a formula. It's a very simple formula. You can actually read this. This is what the computer was doing for us yesterday when it was coming up with sample sizes. So let's look at this. So I have mu1 minus mu2. This is the effect size, or the difference that I would hope to see. So if you don't think a 1-point difference in cholesterol is meaningful, you get to decide what the difference in cholesterol is. You decide that. So if you think a 10-point difference in cholesterol is meaningful, then put that down at the bottom. So remember yesterday I was telling you, you don't have to know what the actual values are. You can put a 0 and a 10, because the 0 and the 10 gives us the -10. This is why. And the other thing we talked about yesterday was we were interested in looking at the variability in the outcome. That's an important ingredient here. So this is the variance for one treatment versus the variance in another treatment. But we assume homoscedasticity, so we could just say 2 times sigma squared. And then we have z1 minus alpha divided by 2. What do you think that is? So if alpha is 0.5, what does this correspond to? So this would be alpha, this would be 0.25, 1 minus 0.25 gives us 1.96. So this is the z-score that corresponds to the 97.5th percentile. And then I have 1 minus beta. What's 1 minus beta? That's power. Right? That's power. That's the probability of rejecting a null hypothesis if it's false. Okay? So that's actually what the computer was doing for us yesterday. Okay, then we talked about coming up with different scenarios. We talked about changing your assumptions. This is what's called a power curve. A power curve. So if you change your assumptions, so D here is our effect size. What happens? How many people am I going to need to reject the null hypothesis at the 0.5 level, given some level of power? All right, so what we see here is that when we have a very large effect size, a half a standard deviation difference between the groups. This is what we did yesterday when we had like a standard deviation of 0.2 or whatever it was. And the difference between the groups was like 3 standard deviations. Remember that? We needed 1 person. This is what happens here. You don't need very many people. When your effect size is small, when you don't expect a very big difference between the groups, you need a whole bunch of people to achieve the same power. The reason that we're showing you this power curve is that this helps inform you as to how much it's going to cost you to do your study under different sets of assumptions. And I did this in Stata. Okay? All right. So let's stop here. We'll pick this up next week, and then we'll pick up multiple regression.